2 of our significant digits in scientific notation assignment. Before you begin, I want to make sure that you watch this video, which will outline everything we're about to do, provide some examples, and demonstrate process. Now, these questions you're required to extract from the video, but there are a few problems pictured below here that I would like to look at with you in particular. The first is 100.0 seconds, and we're converting it into scientific notation. So scientific notation always involves a single digit in the ones place, and all remaining digits trail the decimal. We multiply this by 10 to some factor. So we need a single digit in the ones place, all remaining digits trail the decimal, and then we need to multiply by 10 to a power so that it is an equal value in scientific notation to the standard notation. In this case, we want to make sure that we're able to identify which digits are significant. So zeros that trail the decimal are significant. All non-zero digits are significant. And all digits in between significant digits are significant. So in 100.0 seconds, in this measurement, the error in the measurement is in this final digit. That's the final digit of the measurement. This means that all of our digits need to be included. When we're determining how to move our decimal, we need to move it 2 positions to the left in order to set it up in our scientific notation format. Now, because we moved it 2 place values to the left, we get 2 place values smaller. We need to multiply it by 10 to take up those 2 decimal points, or those 2 place values, I should say, to balance this out. So 1.000 times 10 to the 2 is equal to 100.0 seconds. Now, if you're using a calculator, notice how it'll always truncate off that trailing 0 after the decimal. Calculators are going to do this. We need to identify when a 0 is and is not significant. If we want to use the scientific notation key, we're looking for this key, the times 10 to the x key. Your calculator may vary. Your calculator might have an EXP key. It also might have an EE key. All of these keys are the same function. They're just different brands of calculator. They use different symbols. But the EE, the EXP, and the times 10 to the x key all represent that same function. So if we were to put our scientific notation value into our calculator, that's 1.000 times 10 to the power 2, we get our answer. Next, if we're expanding a value, 3.0 times 10 to the 8, this means that the standard notation value is going to be 8 factors of 10 larger than 3.0. So we're going to move the decimal point 8 places to the right. So that's 1, 2, 3, 4, 5, 6, 7, 8. So that's 8 positions to the right. We have our value in meters per second. Oh, reminds me, this was in seconds. I like to use the cursive S because my S's sometimes look like 5s. Just something that it's probably wise for you guys to adopt. Let's double check here. If we have 3.0 times 10 to the 8, we get this value. Now the problem that we run into is in 3.0 there are 2 significant digits. In standard notation, it's really hard to express how the 3 and the 0 immediately after it are both significant, but all of the remaining zeros are placeholders, not significant. Scientific notation is a great way for you to express the precision of a value. In this case, the precision is 2 significant figures. Standard notation, it becomes rather difficult to express which of these digits is and is not significant. On the back side of our worksheet, we have some calculations that we're going to perform, and we're going to use our previous skills. That is, working with scientific notation and rounding to the appropriate number of significant digits. In question 6a, we're given that a 50-gram weight displaces 12.7 milliliters of water. What is the density in grams over mils? In this case, the unit of measurement of density is the equation that we're going to use to solve for the density in this question. So in this case, we're given a 50-gram weight and 12.7 milliliters of water. Our density, D, is going to be equal to our mass divided by our volume, which in this case is 50.0 grams over 12.7 milliliters. When we divide 50.0 by 12.7, we get a value of 3.937, a whole bunch of numbers there. The unit is grams per mil. If we look in our equation, grams over milliliters is in our equation. That is the unit of our final answer. The question becomes, how many significant digits do we need to round our answer to? Now, as we learned in the previous section, when multiplying or dividing, in this case we're dividing, our final answer needs to be rounded to an equal number of significant digits as the least precise component of the calculation. In this case, 50.0, the 5 is significant, the trailing 0 is significant, the 0 in between, therefore, is significant, so that has 3 sig figs. 12.7, all non-zero digits, also 3 sig figs. Our final answer must have 1, 2, 3 sig figs. Our question at the bottom of the page here, we're subtracting 2.5 times 10 to the minus 6 from 1.35 times 10 to the minus 5. We're subtracting 2.5 times 10 to the minus 6 from 1.35 times 10 to the minus 5. If we're doing this in our calculator, that's 2.5 times 10 to the negative 6. So that's that value, how you would express that. Or 1.35 times 10 to the power negative 5. That's how you would punch that into your calculator. If you're using a different calculator, 2.5 times 10 to the power negative 6. That's how we would express that value. 1.35 times 10 to the power negative 5. That's how I would express that value. So we're subtracting 2.5 times 10 to the minus 6 from 1.35 times 10 to the minus 5. So it's 1.35 times 10 to the negative 5. This is a direct algebraic input, so negative 5. There we go. And we're going to subtract from that 2.5 times 10 to the power negative 6. We get our answer, 1.1 times 10 to the minus 5. However, calculators are always going to truncate off trailing zeros. That's just what calculators do. Let's take a few moments here and let's see if we can do this by hand and figure out how much precision this value should have. We can't subtract these two values because our powers of 10 don't match. But there is something we can do. We can write this value in a different way so that they have the same base 10 factor. Let's take a look at what that might be. So we'll make this value 10 times smaller, and we'll make this value 10 times larger. So that these two values are equal, and now they have the same base 10. When we subtract these two values, We have 1.35, subtract 0.25. We get 1.10 times 10 to the minus 5. We always want to make sure to round it to the least precise place value, which in this case, when we have our factors of 10 equal, is the hundredths place of our scientific notation values. So 1.10. If we were to do this another way, and expand out 1.35 times 10 to the minus 5, and expand out 2.5 times 10 to the minus 6, we get the same value. On our dimensional analysis assignment, the first thing I want you to do is watch the video linked at the top of the document. After you watch this video, we've demonstrated the skill of dimensional analysis, and we're looking for you to demonstrate those skills in the calculations below. In our first example, we have 10,000 seconds. We're looking to convert this value into minutes. Something to keep in mind when you're making your conversion factors, the unit you're solving for is always on the numerator. That's the unit we want, minutes. The unit we started with, seconds, needs to end up on our denominator. And then the relationship between these two values is what's called an equality. So for example, 1 minute is equal to 60 seconds. This is an equality. Our equality gets placed inside our conversion factor. We look to see that our units cancel. They do. The only unit that remains is minutes, which means our final answer is measured in minutes. We can punch this into our calculator. We get our answer, 166.6 repeating. Now, when we have an answer that's in standard notation and is all trailing zeros, we have to assume that all these zeros are not significant, that this precision includes only one significant digit, which would mean that 10,000 seconds is about 200 minutes. All right, this is a complex unit, 50 kilometers per hour. There's two units involved, and we're looking to convert both of them, kilometers into meters and hours into seconds. Let's make a short list of the equalities we'll need. We need an equality for kilometers and meters. 1 kilometer is equal to 1,000 meters. Now, to convert hours to seconds, I don't know how to convert those in my off the top of my head, but I can go from hours to minutes and then from minutes to seconds. So "50 kilometers per hour." That's our given value. We're looking to convert it to meters per second. So let's first convert kilometers into meters. We want meters on our numerator. We have to get rid of kilometers. So they're on opposite sides here. 1 kilometer is equal to 1,000 meters. Our kilometer units will cancel out. The units that remain are meters per hour. So if we multiplied 50 times 1,000, we would have 50,000 meters per hour. That's not what we're solving for. We're solving for meters per second. Now, I don't know how to go from hours to seconds in one step, but I do know how to go from hours to minutes. So let's eliminate the hours unit by putting it on opposite sides. If it's the denominator here, we'll put it on the opposite side here, the numerator. 1 hour is 60 minutes. Because they're on opposite sides, numerator and denominator, they'll cancel. If we multiply this through now, 50 times 1,000 divided by 60, we would have meters per minute. But we're not solving for meters per minute. We're solving for meters per second. We want seconds on the denominator, so place it on the denominator. Minutes is the unit that we're looking to eliminate. 1 minute is 60 seconds. Our minutes will cancel. The only units that remain are meters in the numerator and seconds on the denominator. So meters per second is the unit of our final answer. If our units don't cancel, we have some bizarre looking unit here, we've made an error. Go back, figure out what the error is, make the correction before you report your final answer. We have 13.8 repeating. Now 50 kilometers per hour is not a very precise measurement. Because this is a trailing zero and a non-decimal number, we're going to have to assume that there's only one significant digit. So this is about 10 meters per second. That's the maximum precision we can report our answer to, given that the information we put into this was so imprecise on its own. All right, that's how to work with dimensional analysis to accomplish a relatively challenging conversion. Good luck, give them a try, show me your progress. Talk to you again soon.